Assalamu alaikum and welcome to this recorded lecture. As I sent you over the email, I thought, well, based on previous experience, that it is more suitable to record this lecture so you can study it at home. I know that last Monday the lecture was not included in the midterm exam, so I expected very low attendance and the topic was not going to be studied thoroughly. So this way, I think it is better. What is this lecture about? So the topic now is the channel. Let me put you in perspective. So we have seen that here, wherever we have the transmitter, we have seen the chain that we have here, the data that comes with, then it is sampling here, whatever the box is, then the signal was transmitted here and we have the RF. At the receiver side, we said that the first thing the receiver will do, will take the signal from RF to baseband. Then everything here has an opposite one, or a compensator. So if there was a mixer here, so here this will be the D mixer. If there was a modulator, D modulator, and so on until we finally have here the whatever we said here, hi, how are you? We receive again the signal. So here the analog signal sent, analog signal received, and ideally they are the same. So whatever you will send, the other side of the communication will hear it. Good. Something that we have missed so far is what happens here in between. So whenever we send the signal until it is received by the other one. So here, what's happening here in the channel? So this will be our topic now. We want to study the channel. And whatever are the properties for the channel. So the channel could be different classifications we could have for the channel. But yeah, it could be wireline, it could be wireless, it could be underwater communication. Yeah, it is a big field. Whatever is the link. Here in our course, our main consideration will be the wireless, with all the problems with the wireless and so on. It is not the most complex. This one it has its own problems also. This one also has its own challenges. But yeah, this is the one that let's say it is the one that is widely used. The wireless examples. Wi-Fi system. Whenever we would like internet at home, we have all the family of 2G, 3G, 4G, 5G, hopefully soon 6G. We have the LoRa system, LoRa 1. Maybe some of you or will do the SDP project in them. We have satellite also here within the wireless link. We have the microwave link, microwave communication, all of them wireless, and others. The remote control of the TV, the remote control RF for the car, whatever, anything that you would like to communicate over wireless. So yeah, it is a very large field. The concentration of the course is on it. Good. So then now we can say that, it is the channel. More specifically, it is the wireless channel. The wireless channel is not better or worse than wireline. It simply has some advantages that you as an engineer will decide if it is a suitable one. As a rule, the rule says always use wireline if available. Communication over wireline much easier. So the example, you have let's say a secretary, with a desk, and there is a laptop on the desk. So he or she, the secretary, is working always on the same place. on the desk, the laptop is on the same place. So what will be the best way? Connect the laptop with the wire to the socket so that you will have internet. Good. So in that case, wireline is the best. Okay, the data rate is huge, the quality perfect, and everything good. When you will need to go wireless, okay, so the wireless, there is a keyword, okay, that goes with wireless, and it is called mobility. Even in some spots for the providers, Ooredoo, Vodafone, okay? This is usually a keyword, okay? Because if you are not moving, you don't need wireless. If you are on sitting on the same place, wireline will be much better, okay? So whenever you need to move, okay, so you will need wireless. You cannot move with the wire, okay, hanging. Definitely, there are other advantages for wireless, okay, but yeah, this is the main one. So whenever you want to move. Good, so mobility and wireless are highly related. So then going back here, this is the motivation and so on. So whenever now we want to see, we want to study this wireless channel. So the wireless channel, whenever we study the wireless channel, so there are so many classifications, okay? First of all, the model of the wireless channel, okay? It could be indoor or outdoor. Well, main ones, okay? There are others that say, okay, partially outdoor and so on. But yeah, these are the indoor and outdoor. Example for indoor, the best example is the Wi-Fi router. So inside the classroom, we have a router here hanging or wherever, in any place, and we have some people here using the internet. So this channel is completely different from this channel. Whenever here we have a building, and on the top of the building there is a tower for Ooredoo, Vodafone, or whatever, okay, and you could be here inside another building, okay, and this guy wants to have access. Good. So what are the differences? Whenever we have an indoor channel, usually the communication is direct, okay? So here, usually the transmitter, which is here, or in our case here, transmitter, and this one here, the receiver. It could be the reverse, so maybe you are uploading something. So you will be the transmitter and the router will be the receiver, okay? So here, the link, usually it is, we call it visual. So the transmitter and the receiver, they see each other. The official name is called line of sight, okay, or LOS. So whenever you will hear, and this is a word that is used a lot in the field, we have a LOS. No, wallah, we don't have, and so on. Good. So here, whenever we have LOS, it means that you can visually, okay, the transmitter receiver, they can see each other. That does not mean that there will be no reflections. Yeah, there will be reflections. So here the signal could be reaching from here, reaching from here, reaching from here, and so on. But yeah, there will be a major one, which is this one, the direct one. On the other side here, we could have non-line of sight. So here, the non-line of sight, okay, or the N-loss, or no loss. So here we don't have line of sight. This is a very common whenever you are outdoors. Usually whenever we are talking with your phone, you don't see the tower of Ooredoo or Vodafone. Here the signal will do like this. Reflection, maybe here there is another building that will do like this. It will enter from here. It reflect wherever, then the signal will reach you. Good. So here, the non-line of sight, as I repeat, we don't have a direct link between the transmitter receiver. LOS is not better than no loss. No loss is not better than loss, okay? But we need to know how to deal with each one of them. So whenever it is, the signal is lost, the signal propagation is lost. So here what we will have, so imagine this is the time axis, and here this is the power. Okay? So here, this first one, so here imagine that this, we call it 1, then this is 2, this is 3, this is 4. Okay, so the signal will reach the receiver 4 different paths. The first one, the loss, the second one, third one, fourth one maybe. So this will be T1, T2, T3, T4 with powers P1, this one P2, this one P3, and this last one P4. Good. So here this will be the characterization of this one. So here you see that almost all the power will come from the main. Each one of these is called paths. Okay, so here we have several paths, but yeah, the loss, the LOS path, it will be the one with the highest received power. So here in this case, the receiver can only take care of this. This is what is important for the receiver. Okay, all these others, yeah, it's good to receive them. They will increase the power, but yeah, they are not that important. Okay, the important one is this one. On the other side, whenever it is no loss, then also here the signal could be received with many reflections and so on, from here, from wherever. So, but usually the different paths. So let's say here we have 4 paths. Here let me also consider 4 paths. Again, time versus power. The first path could be this one, the first, the second, the third, and the fourth. So here it will be T1, T2, T3, T4. All of them received with very similar powers, because all of them, every one of them, it went through reflections. Okay? So here, whenever we have reflection over this building, okay, so some signal is absorbed, some will be reflected, we have some loss. The other one here, they will be loss. So all of them, on average, they will have losses, and the losses will be very similar. Okay? So here we don't have a dominant path, let's say, okay? While here we have a dominant path. So here, let's call it dominant path. Here we don't have a non-dominant. Almost all the paths are the same. Usually they are decreasing, because whenever you spend more time to reach, okay, it means that you spend more distance. You know, D equals C multiplying T. So this one, it took more time to reach through this second path, which means the distance that it traveled, it's larger, because the speed of light is the same for all. Okay? So if it traveled more distance, it would have lost more. Is it a must? Not necessarily. Okay, we could face, let me change the color. We could face a channel profile, okay, that is like this for a certain time. What happened here? We don't know. Maybe the first path, it has been, it went through a wall of concrete, while this second path, it went through, reflected through glass. Okay? Here in Daphna area, we might face this a lot. Okay, if you are working as an engineer and a communication engineer there, okay, you might see channels like this. You say, come on, how is that? This has traveled for more time. Yeah, but this one, it went through, let's say, harsh reflections, or harsher than this one. Okay, let me repeat again. This one, okay, even it took less time. So T1 here is less than T2. But yeah, it might have been with reflections over concrete or aluminium or whatever is the material here for this building or obstacle, while this other one, it may enter through glass, and the glass is a much better reflector. Okay, so it will reflect more power. Then this is why here it could be more power than this one. So again, it is typical one, it is decreasing, but yeah, we could face this other one. This, by the way, this is whenever we have the paths, okay, and we have them with power with respect to time. The official name is that this is called the channel profile. So this is how is the channel, okay? We are having information that is given to us about how is the channel, okay? And again, very important information, whenever it is loss, so here we will have a direct one, okay? Whenever it is no loss, they will be close to each other. Again, whenever it's loss, and I did it on purpose, you see here the time, because it will be the shortest time, okay? It's a direct one from the transmitter to the receiver. So it will be received with the least time compared to this larger time here for the first path. So here the first path will arrive much faster than the first path in the non-loss. Good? We could have even a channel like this. Only one path. Do you know what will be that system? That has only one single path. So it is only line of sight. Okay, two main examples. The first one, you remember when we talked about microwave communication? This, let me remind you, whenever you have a tower of Ooredoo communicating to another tower, the two of them, they are not moving, okay? So here, this is a building, another building, so they design them so that they see each other with no reflection, okay? So one single path, so it will be this one. The other example is whenever it is satellite communication, but yeah, not any case of satellite. Has to be geo. Let's say for TV, for example. So whenever you receive the signal of BN, for example, over satellite, it is transmitted from SailSat 1 or 2. Okay, it is a direct path from the satellite to the satellite dish receiver that you have on the rooftop. Okay, again, one single path, no more paths. Okay, so imagine like this is the satellite. Okay, SailSat. This is your home. Okay, and this is the dish receiver. Where the reflections will come from? Okay. There is nothing here or here or here. That the signal goes directly like this. So here it will be again one single path. So here these two systems, they are characterized by having one single system. Both of them, they have to be LOS. Otherwise, they will not work. Systems that are non-LOS, so here all the systems like 2G, 3G, 4G, 5G, all of them. So here this one, but these, they are called, the official name, they call them cellular, because more than one cell, okay? The cellular communication is always no loss. Wi-Fi systems could be loss or no loss. How is that? Here we said the example that here you have the transmitter of Wi-Fi. You are here, you will receive the signal. But actually, if you go outside the room, okay, you also will get a signal. So this is why the Wi-Fi, it is something hybrid, okay? Not necessarily it is loss, okay? It could be no loss. But by the way, the word loss sometimes is confusing, okay? It is not the loss of signal that is disappearing. It's another way, okay? So here, it's LOS. What else can we base the characterization of the channel on? Okay, if it is, for example, what time correlation. What is the time correlation? So the channel, usually the letter of the channel that's is H. Okay, so H at T1, okay, will be equal of H at T2 whenever T1 and T2 are not the same, which means that the channel now and the channel after, I don't know, 5 seconds is the same. Why 5 seconds? I don't know, 5 hours, 2 milliseconds. Okay, so here, so if it is the same, okay, then we will say that the channel is correlated because now and after some time, okay, it is very similar. Okay, so we will say it is correlated in terms of time. If it is not, then we will say the channel is uncorrelated. So here it could be correlated channel. time correlated, because we have another case, time correlated channel or time uncorrelated channel. Being correlated or uncorrelated is not good or bad. It is just a characteristic that we as an engineer, we as engineers, okay, we should be aware of, okay? Whenever we design our system, we need to know if the channel is time correlated or time uncorrelated. By the way, the channel could be, so imagine that T1, T2, T3. So imagine the T is 0. So here this is 5 seconds, and here this could be 1 minute. So from here to here, it might be correlated. So the performance is very similar, but from here to here, it is uncorrelated. So and there is no one. This channel is correlated. No, you have to tell us it's correlated over our scenario. It is uncorrelated or whatever. Okay, so you have to be specific, depending on what is your application. Okay, so if your application needs that the performance now, you have to compare it with the performance after 5 seconds, 5 milliseconds, 2 milliseconds. Okay, or the performance now. Okay, and you have to check it after a longer time. So the same channel could be correlated and uncorrelated depending on what is the time frame that you are considering. Good? What is the advantage of having the system to be correlated? So it will be the same. So if you so imagine here, this is correlated. So if the channel H at what we call it T1, it is similar to the H at T2. So whatever processing, whatever engineering you do to deal with the channel at this one, it will be the same as this one. So you don't have to repeat again everything that you have done. What is the kind of modulation? What is the kind of channel encoding? What is the kind of whatever? Okay, it will be the same. So whatever you did here, you will do it here. So the advantage is that you don't have to repeat, okay? So it will decrease the complexity. The disadvantage, maybe the channel was bad here, so it will remain to be bad. So it will give you less degrees of freedom. So here, advantage, whenever it is correlated, same performance with same decisions. So less complexity. Disadvantage, what we can write, maybe it is bad. So it will be bad for long time. Here the conclusion is, this is what we call less less degrees of freedom. So whenever you design, you are stuck. Okay, wherever it was bad, so la hawla wa la quwwa. Okay, it will continue for a while to be bad. So this is the disadvantage. Okay. So here, this is whenever we say correlated. Again, being correlated, not good or bad. It is just you need to know that it is correlated so that your design, whenever it is correlated or uncorrelated, will be different. We will see, okay, what to do whenever it is correlated or uncorrelated. Related to this correlation, there is something called coherence time. Capital T with a small c, coherence time. So what is the coherence time? The coherence time has a definition, is how frequent the channel changes. So here we said that the channel could be correlated and uncorrelated at the same time. So here, who decided this 5 seconds? So this coherence time, it will tell you, so here this is the channel, this is the channel, it will be the same, then it will start changing, so it will measure how much the channel will be the same, okay? Or in other words, when the channel will change, okay? So how frequent the channel changes. So this TC, it could be 2 milliseconds, for example. So here it means that the channel is continuously changing, okay? So let me open a new slide. So if this TC is 2 milliseconds, it means that the channel is like this. Okay, and here whenever it is T in milliseconds, so every time it is changing, the channel is continuously changing. It could be TC equals 20 milliseconds. So here the rate of changes will be less. It could be 1 second. So it will be like this. So the rate of change much less. It could be 1 hour. And so good. So here the rate of change much less. Now let's put systems, okay? So whenever the coherence time is 2 milliseconds, okay? So not 2 milliseconds, but to be more practical, for example, Wi-Fi systems, they have measured the coherence time to be 4 milliseconds, as long as I remember. 4G, for example, okay, they measure the coherence time to be 20 milliseconds. Who is 1 millisecond? Who is the system that is 1 millisecond? I would say microwave, maybe. Microwave is a good example of having a system that is 1 second. And who could be 1 hour? I cannot imagine a wireless. Yeah, here it could be a wire line. A wire line, okay? The channel in the wire line changes very slowly. Why? The channel, it is the same. So it is the same copper or the same whatever material for the wire line. So the channel changes very slowly, okay? So here, this is the coherence time. Also here, it is the role of the engineer to deal with this coherence time. Usually the coherence time, how to measure the coherence time? By testing. Okay, so we will put a device, okay, moving around, making measurements for a long time, okay, and then we go to MATLAB, we analyze the system, we will know how frequent does it change, we will know, okay, the value. For the 4G, for example, how they used to do it, they hired taxi drivers, Carwa, for example. They put transceivers on their cars and they tell, okay, move around for 1 month. Then we will collect the information back. After 1 month, they collect the information, they analyze that information, then they realize the value is 20 milliseconds. Okay, based on that information, they design the system. So here, whenever they know that it is 20 milliseconds, so the channel for the 20 milliseconds, it will be the same. If it was bad channel, it will remain to be bad. If it was good, it will remain to be good. Okay, so here, in 20 milliseconds, we can allocate, I don't know, 100 users maybe, okay? So if they are here, then you know that these 100 users, they will have a bad channel. They will have a good channel, and so on. Good? All of this also we will see it whenever we will make designs for the system, okay? This coherence time. Now here we are just studying the characteristic, okay, without any design. Another feature for the channel is correlated, but now here space correlated. So this is spatial correlation. What does it mean to be the channel to be spatially correlated? So here we have the Ooredoo tower, for example. You are this customer, and here there is another customer, maybe your colleague, okay? Here the signal, most probably the one that you will receive, will be very similar to the signal that your colleague standing next to you will receive. Good? Maybe even it is not direct, even here I draw it as a line of sight, but yeah, let me remove, okay, both of these. Even in the case that Okay, here imagine you are inside a building, so this will go like this, it will reflect and then it will reach you. Most probably the signal for your colleague sitting next to you, okay, will do the same. So in this case, we say that the signals, okay, or the channel between user 1 and user 2, so here this is H for user 1, okay, is very similar to the H of user 2. Okay, in this case here we say that they are spatially because of space, okay, spatially correlated. Again here, the engineering done, okay, on your signal will be very similar to the engineering done on your colleague signal. Right. Do we have always correlated? You say, come on, yani, two guys next to each other, it will be the same. No. So here, whenever we are indoor, so here this is the room, this is the router, these are two colleagues sitting next to each other. The signal for the first could be like this. The signal for the second could be like this. Completely different channels. So usually in Wi-Fi, usually it is completely uncorrelated. While in outdoors, it might, not necessarily, might be correlated. Also depends on the scenario, okay? For example, let's see. Oh yeah, here in Daphne we see this a lot, okay? So, especially whenever we have a city that is grid-wise. Streets and parallel and so on. So here, imagine this is the Ta'awun Street, okay, in Daphne. So they put a tower here. This car, or this car, or this car, most probably they will receive the same signal, okay? So even it comes with reflection. So here you will say that, yeah, I have to be a better drawer, okay? But yeah, here we have one building, another tower, another tower, another tower, you know, okay? So here the street, and it is surrounded by towers on both sides. So here, whenever the base station will transmit to the first one, it will go through reflections, the second one also reflection, third one also reflections, okay? And also for the first one, maybe the reflections will be like this, which means that, okay, any car here on the street will receive reflections over the many towers that are on both sides. And the signal for each one of them most probably is very similar, okay, because of the reflections, okay? So here, this case, the channels usually are spatially correlated. Again, let me repeat. It is like a waveguide, or what we call it. To be it's like a corridor. Yeah, corridor. Very nice. So here, all the signals, okay, received by everyone here, it is like a corridor. So here, all the signals reflected on both sides, and it is the similar one. The reflection for signal user for user 1, it will go through these towers. The signal for user 2 will also go for the same towers. Okay? So here in this case, we will have it like this. It is like, imagine that, for example, I like this corridor. Okay, so here, this is the corridor inside the house, and here, this is your room. Good, and imagine that the Wi-Fi router is here. So the signal for two people, even they are not close to each other, okay, but they are in this same room, the signal from the router, Wi-Fi router, it will definitely go like this for the first, for the second, okay? So for 90% of the distance, it is exactly the same path. For 10% here, it has changed. Let me repeat, because this 90% or 10%, I know it could be confusing. So again, let me draw it. So here, this is inside the house, okay? So this is a corridor. Here it could be another room, but yeah, the doors are closed. And here we have this room with the door open. You have this guy here, another guy in the same room, but yeah, not sitting not sitting next to each other. The Wi-Fi router is here. So the signal for the first one, and let me change the color, will do this. And it will reach here. The signal for the second one, because here nothing changed inside the corridor, so it will do exactly the same. But now it will come to this user. Good. Now here, the both signals, and let me change the color to again to what? No, to green. Good. So the signal over this distance. So I imagine that the distance from here to the room 10 meters. Okay, so for 9 meters, both the blue and green, they did exactly the same. Okay, here inside the room, definitely they are not the same. Here for the last 1 meter, they are definitely not the same. So here we will have that for 90%, they are correlated. So definitely they are spatially correlated. For 90% it's the same. For 10%, completely different. So in this case, we will say, yeah, it is a spatially correlated channel. Again, to know it is spatially correlated is very important, okay? After you know it is spatially correlated, you need to design, okay? But so far, for now, we are just describing, okay, what could be the channel. Later, we will see, okay, how to design based on this information. The last, well, there are so many, okay, characteristics that we can characterize the channel based on, but yeah, the last one that we will describe now is the frequency. Yeah, let's go black. So what is the operating frequency? Okay, based on the operating frequency, the channel will change. Examples, even for this is the room, Wi-Fi router, you are here. I told you last time that here, and you know this, okay? So whenever you would like to connect to Wi-Fi, yeah, the network could be, imagine that the network is called net. So this will be net and net 5G. Most probably you have this feature at home, okay? So you could connect to the same network. You call the network Ahmad, Muna, Saeed, whatever is the name of the network, okay? Usually it is the name of the network and the network 5G, especially if you are close, you will detect this one. So here, the channel, okay, it will be different from A to B because we have changed the frequency. I told you last time that this 5G is a tricky one. Okay, it should be 5 gigahertz, it's not 5G. So here, this one, it's not stated, but it is 2.4 gigahertz. So the channel for connection 1 or Wi-Fi A, let's call it, okay, it is operating frequency is 2.4 gigahertz, while for B, its operating frequency is 5.3, I think, okay, gigahertz. So here, it is the same guy, same location, same everything, but yeah, the channel, this channel will be completely different from this channel. Okay, so here, why, what has changed? What changed is the frequency. So here, the operating frequency is very important. It will change everything. Obviously, well, it is a parameter that, for example, if the frequency is 900 megahertz, if you go to the 910 megahertz, it will change. You have to check. Oh yeah, we call the other one what we call coherence time. Here there is something called coherence bandwidth. So what is the coherence bandwidth? What we have defined the coherence time, okay? How frequent it will change. So here the same. So coherence bandwidth if this is the channel, let's say, now here this is frequency, and this is, let's say, received power, then we will say, and let me change the color, that for example, all of these frequencies, they have the same performance with a 99.9% approximation. So here, the frequencies from F1 to F2, they have the same performance. F2 minus F1 is the bandwidth. So we will say that the bandwidth, coherence bandwidth for this system operating at whatever, okay, is, I don't know, 100, what was our example? 10 megahertz. Well, it's impossible, but yeah, based on our example. What are typical values for this coherence bandwidth? Coherence, for example, in 4G, because I remember it, it is 15 kilohertz. So each 15 kilohertz, we can assume the channel to be the same, exactly the same. From 15 kilohertz to the next 15 kilohertz, it will change. Okay, so here, this band, okay, it will be 15 kilohertz. So it's like the channel we can approximate with the 99.9%, okay, that it will be like this. We are like kind of discretizing, okay, the channel. So each 15 kilohertz, it has exactly the same performance. This has been measured in 4G. Again, how they have measured this value, the coherence bandwidth, field test. Okay, again, the Carwa example. They put cars to drive or people and so on. They take measurements and then they decide what is the value. Usually it is much more, but yeah, to be on the safe side, they go to a safe value. And for example, this is in 4G. In order to do it, they had to do measurement in so many places around the world. Okay, some cities that are hot, others that are cold, because they can affect the channel, the temperature, humid, non-humid. We will see all of this, okay? What else? Above the sea level, on the sea level, and so on. And they take the average, okay? And then they go to the worst case, okay, to be on the safe side. They found it to be 15 kilohertz. So based on that, they designed the system. We will see, okay, whenever we will design the system, okay, what is the impact of this value. But yeah, for now, as we are just commenting about the properties of the channel, this is enough to say that, yeah, this is what we call the coherence bandwidth, okay? So it will be the band that the channel performance will be the same within it, okay? Or how frequent the channel will change over the frequency. So each 15 kilohertz, the channel will change. And if you are operating at this frequency or this frequency, definitely the value for the coherence bandwidth is different. Oh, very good. That I came to this question because many students still confuse between them. Frequency is not the same as bandwidth. Okay, very important. Okay, and whenever, if I correct in the exam or quiz and I see that you make this mistake, okay, I will stop correcting, okay? No sense. Frequency and bandwidth are not the same. The operating frequency is the 2.4 gigahertz, for example, for the Wi-Fi, but the bandwidth could be on that band, well, too much. How much is the one? 25, 30 maybe, 30 megahertz. What does that mean? Okay, so this system, the Wi-Fi one, we always say it is at 2.4 gigahertz. You know 2.4 is 2400 megahertz, okay? So this is the operating frequency. So here, usually this is the central frequency, which means that the system actually, if it is 30 here, so it will be, the system is from 2385 megahertz up to 2415 megahertz. Okay, so here you see, did I did the math correct? 15 or 15, yeah, 30. So here, this is the band. The band that is given to the system is 30 megahertz. Its operating frequency, usually they select the central one, is the 2400 megahertz or the 2.4 gigahertz. So we could have large frequency. We could have large frequency with large bandwidth. We could have a small frequency with small bandwidth. We could have small frequency with large bandwidth. You see, so they are not related at all. Okay? How much the bandwidth and how much is the operating frequency. So here at 2.4 gigahertz, this could be the band. They could have another system, okay, I don't know, cellular for example, okay, it is at 900 megahertz. This is for the 2G. It is actually from the 910, if I properly remember, up to 990 megahertz. But yeah, the engineer always they say, okay, this is at the 900 megahertz because there are others, okay, for the 2G. But yeah, you see here, 80 megahertz of band. Well, even it has some gap in between. But yeah, for our example, for easiness, okay, it is 80 megahertz of band. So here, yeah, we have, it is the frequency, operating frequency is less, but the bandwidth is more. So they are not related, okay? So the bandwidth, it is, as you have seen in signal system, it is F2 minus F1. This is usually the equation that give you for the bandwidth. So it is F2, the final frequency, minus the initial frequency. This is the band that you can deal with. At what is the operating frequency? What is the central frequency? I don't care. It could be another value. Okay, so the frequency has some effect or impact on the system. The bandwidth has another impact that has nothing to do with the frequency. Good? So again, very important here, the difference between frequency and bandwidth. Okay, so I think we are good, okay, in the characterization of the channel. Whenever we will see OFDM design, we will see how to benefit from all of these properties of the channel and the design, how to exploit them, how to benefit from them, how to be aware of them. But yeah, all of these characteristics, okay, are important before we start into the design. By this, we will cover the channel for at least the characterization of the channel, what we need now. Next lecture, we will be moving to the receiver side. So we will cover the receiver side in the next lectures. Then we will move to the design, okay? And in the design, we will take benefit from everything that we have seen so far. Transmitter, channel, and receiver in order to decide what is the best design. So I will stop here. I think the time is good. Definitely, the lecture could not be 1 hour and 15 because in the lecture you ask, there is more time that is spent, while here it is a continuous, okay, explanation from my side. But yeah, I think that whatever we have explained is fit, okay, for the 1 hour and 15 minutes of lecture. To guarantee that this lecture is studied, okay, I will be announcing a quiz soon, okay, so that you study this one and then you can continue with the flow of the material. So I will stop here and see you in class inshallah. Assalamu alaikum.